So in this problem, we're asked to determine what is the moment caused by the force, 300-pound force that goes from point C to point D about the OA axis. Okay, so we can define um, uh, we can define our moment about the OA axis using this equation. Okay. So first things first, let's define each component. So UOA we can define using the coordinates of O and A, so that would be equal to ROA divided by the magnitude of ROA. ROA, we know R is going to be equal to RA minus RO. The origin has no value. It has the position vector of the origin has no value, so it's just going to be equal to RA. And then if we look at the coordinates of RA, it's going to have 0.3 meters along the x-axis, and it's 0.4 meters along the y-axis. All right, and then there's no component along the z, and then we can divide by the square root 0.3 meters squared plus 0.4 meters squared, which should give us 0.5 meters for the total length from point O to point A. So U of A would be equal to 3/5 times I plus 4/5 times the unit vector j plus 0 k. All right. So then our next step is our position vector r. So you could define r from any point on our axis to where the force is being applied. So you could define r could be any of the following vectors. It could be from RO to point C. It could be from RA to point C. It could be from RA to point D, or it could be from RO to point D. So we're going to use RO to point D, but you would get the same exact answer if you used any of these terms. Okay? They'd all give you the same answer. So we're going to use R from point O to point D. So if we follow our line here, it's 0.5 meters in the x direction, and it goes up a positive goes up a positive 5 meters along the z-axis, but there's no y component. Right. So our last component is going to be our force CD. Right. So our force CD is going to be equal to the magnitude of our force, which is 300 newtons, times the unit vector UCD. So UCD is going to be equal to R of D minus R of C, which is the same thing as RCD, divided by its magnitude, the magnitude of that vector. So give me a second here. There. All right. So R of D is at so point RD is equal to 0.5 meters I plus 0 meters in the y direction plus 0.5 meters in the z direction. Alright. and then the R of C is equal to 0.1 meters in the x direction. It is equal to uh, uh, 0.4 meters in the y direction, and it's equal to 0.3 meters in the z direction. Right? So if we take those differences and square them, we will get 0.4 meters squared plus 0.4 meters squared plus 0.2 meters squared. All right, which would be equal to 0.6 meters. So we would get UCD would be equal to 2/3 I plus negative 2/3 J plus 1/3 K. Right? And then if we multiply UCD by 300 newtons, we would get FCD. So FCD would be equal to 200 newtons, and along the x direction, minus 200 newtons along the y direction, plus 100 newtons about the z direction. All right. So now we're going to plug all these values in to our original equation. So now we have each of the components of our original equation. So we're just going to plug in those components and solve. All right. All right. So, sorry. So the first row will be our unit vector from point O to point A. So we had defined that as being equal to 3/5 along the x-axis, 4/5 along the y-axis, and 0 about the z-axis. The second row is our position vector from point O to point D, which we defined as being equal to 0.5 meters, 0, and 0.5 meters. And then the last row would be our force, which we defined as being 200 newtons, minus 200 newtons, and then 100 newtons. All right. So the first step when we have this determinant is we're going to rewrite the first two columns of our matrix on the right hand side. So if we do that, we'll get 3/5, 4/5 on the first row, 0.5 meters, 0 meters on the second row, and you get 200 newtons, and then minus 200 newtons on the last row. So MOA will be equal to the sum of all the all of these diagonals here. So what we'll get is the first diagonal will be 0. The second diagonal would be equal to 4/5 times 0.5 times 200. So that's going to be equal to 200 newtons times 0.5 meters times 4/5. Alright, and then the last term will be 0. And then we're going to go the opposite side, and we're going to subtract all of these diagonals. So we would get minus 0 for the first diagonal. We would get minus negative 200 newtons times 0.5 meters times 3/5. And then the last diagonal, we would get minus 100 newtons times 0.5 meters times 4/5. Alright, so what we end up getting here is we'd get this is going to be equal to 80 newton meters minus plus 60 newton meters minus 40 newton meters, which is equal to 100 newton meters for the moment about the OA axis. All right. So for these problems, it's pretty straightforward. The order of operations, we first defined our governing equation here, then we defined each of the components of that governing equation. So we defined our u of OA, we then defined our position vector, R, right, and then we defined our force vector. And then once we defined all of those, it's just evaluating the dot product of a cross product, which is sometimes called as the triple scalar product here. All right, and we use this equation here, and we end up getting the scalar value of our moment about our axis.